Hello and welcome to this lesson on simple harmonic motion energies, which is part of the oscillations topic in the module of Newtonian World and Astrophysics for OCR A-Level Physics. So if we've been successful and we've learnt in today's lesson, we should be able to detail the interchange between kinetic and potential energy during simple harmonic motion, calculate properties based on the energy stores of a simple harmonic oscillator, and understand and interpret energy displacement graphs for a simple harmonic oscillator. So we're going to be looking at the following parts of the OCR A-Level Physics specification. 5.3.2, the energy of a simple harmonic oscillator. Now, in all simple harmonic motion systems, there is a conversion between the kinetic energy store and the potential energy store. All undamped oscillators are considered closed or isolated systems where no energy is dissipated to the surroundings. Therefore, the total energy of a simple harmonic system remains constant. So we can say that the total energy is equal to the kinetic energy plus the potential energy, or that the total energy of the system is equal to the kinetic energy store of the oscillator plus the potential energy store of the oscillator. Now, the total energy of a simple harmonic oscillator can also be referred to as the mechanical energy of the system. So as we said, in all simple harmonic motion systems, there is a conversion between the kinetic energy store and the potential energy store of the system. Now, in this instance, the potential energy store is the energy due to the position of the oscillator in the gravitational field, whilst the kinetic energy store is the energy due to the oscillator moving. So if we consider a pendulum displaced by x, amplitude A being the maximum possible displacement from the equilibrium, at this point the pendulum is at its highest point, so the object will have its maximum gravitational potential energy store. So we can say the displacement is equal to A, the velocity we know is 0, and the acceleration is a maximum. Now, if we continue to consider this pendulum undergoing simple harmonic motion, well, at the equilibrium position the object is moving at its fastest, so it's become a maximum kinetic energy store. So we know here that the displacement is 0, the velocity is a maximum, and the acceleration is 0. Now note, the restoring force does work on the object, allowing the energy to change store. If it then moves into our fallen position here, we know at this point the pendulum's at its highest point again, the object has become a maximum gravitational potential energy store again. So again, the displacement is minus A, the velocity is 0, and the acceleration is a maximum. Once again, back at its equilibrium position, the object is moving at its fastest, it's become a maximum kinetic energy store, the displacement is 0, the velocity is a maximum, the acceleration is 0, and then back again to end the cycle, it's at its highest point again, the object's become a maximum gravitational potential energy store with the displacement equal to A, the velocity to be 0, and the acceleration is a maximum. So we can summarise this as the following. You can see where you've got the maximum gravitational potential energy store at the maximum displacements and the minimum gravitational potential energy store at equilibrium. This is then opposed by the kinetic energy store, which is the minimum at the maximum displacement and maximum at equilibrium. Now remember, as it's a closed system, the total energy remains constant throughout the cycle. Now we can show this idea on a graph of energy against displacement. Now this is a graph for half a cycle of oscillation. Now note, displacement is a vector, so the graph has both positive and negative x values, but energy stores is only a scalar, so it can only be a positive value. Now here we can see how the energy stores of the oscillator changes with part of the cycle. Now, for a simple pendulum, there's a transformation between the kinetic energy store and the gravitational potential energy store. At its lowest point, it has a minimum gravitational and maximum kinetic. At its highest point, where the displacement is a maximum, it has no kinetic but a maximum gravitational. So we can see here the points of minimum kinetic and maximum kinetic, and then on here the points of maximum gravitational potential and minimum gravitational potential. Now, it is unlikely that an oscillator will ever have truly zero kinetic energy or gravitational potential energy in a cycle. Now, the potential energy is represented by a parabola or a U-shaped curve, whilst the kinetic energy is represented by an inverse parabola or an N-shaped curve. Now, we can also consider a mass spring system displaced. So a mass on a spring follows the same laws of physics as a pendulum, simple harmonic motion. Now here, as the mass spring has stopped moving, the kinetic energy is a minimum. Now there are two types of potential energy stores in this system, the gravitational and the elastic. So here, the elastic potential energy store is at a maximum, as is at its most stretched, and the gravitational potential energy store is at its minimum, as is at its lowest. Now we know here, the displacement is equal to A, the velocity is equal to 0, and the acceleration is a maximum. Now here we're at equilibrium and the mass spring is now moving at its fastest. The kinetic energy store is at a maximum. Once again, our elastic potential energy store is at a minimum as it's not stretched, and the gravitational potential energy store is still present as it's some way up. We know here the displacement is equal to 0, the velocity is a maximum, and the acceleration is 0. Now at this point, our mass spring has stopped moving, so the kinetic energy store is at a minimum. Now here, the elastic potential energy stores at a maximum, as at its most compressed or stretched, and the gravitational potential energy store is at a maximum, as is at its highest. So we know here, the displacement is equal to minus A, the velocity is 0, and the acceleration is a maximum. Now we come back to being at equilibrium again, where displacement is equal to 0, velocity is a maximum, and acceleration is 0. So here our mass spring is moving at its fastest, and the kinetic energy store is at a maximum. Again, the elastic potential energy store is at a minimum, as it's not stretched, and the gravitational potential energy is still present, as it's some way up. Again, here, at this part of our cycle, we know the displacement is equal to A, the velocity is 0, and the acceleration is a maximum. Again, here, the mass spring stopped moving, so the kinetic energy store is at a minimum. The elastic potential energy is at a maximum, as at its most stretched, and the gravitational potential store is at a minimum, as is at its lowest. So for a mass on a spring, there is still a transformation between a kinetic energy store, the gravitational potential energy store, and an elastic energy store. Now this graph combines the elastic and gravitational potential into one potential energy store. At the top, there's a maximum elastic potential energy store and the gravitational potential energy store, but a minimum kinetic energy store. At equilibrium, there's a maximum kinetic energy store, minimum elastic potential energy store, but there is still some gravitational potential energy store. Whilst at its lowest, it has no kinetic energy store, minimum gravitational potential energy store, but maximum elastic potential energy store. So this leads to a similar energy displacement graph as a simple pendulum. This shows that the energy displacement graph is consistent for one cycle of any simple harmonic oscillator. So once again, we have our points of maximum and minimum kinetic energy and maximum and minimum potential energy. Now for a simple pendulum, we can calculate the values of the different energy stores. We know that the gravitational potential energy store is equal to mgh, and the kinetic energy store is equal to 1/2 mv squared. Now for a mass oscillating on a spring, we can calculate the values of the different energy stores. We know in this instance that our elastic potential energy store is equal to 1/2 kx squared. Now the elastic potential energy is always positive and varies from when it's 0, when x is equal to 0, to 1/2 k a squared where x is equal to a. Now the total energy of a system is when x equals a, because the object will be stationary for an instant. So this means that there's no kinetic energy. The total energy of the oscillator must therefore be equal to 1/2 k a squared. Now the kinetic energy is equal to the total energy minus the potential energy, because the kinetic energy at any instant must be the difference between the total energy and the elastic potential energy. So we can say now our total energy is 1/2 k a squared, our potential energy is 1/2 k x squared, so we can write that as 1/2 k open brackets a squared minus x squared. Now finally, the total energy of a system can also be written as the total energy is equal to 1/2 times by the mass times by the angular velocity squared times by the amplitude times by the amplitude squared. Now we know that this comes from the substitutions on the simple harmonic motion equations of v and x into the equations. Potential energy is equal to 1/2 kx squared and kinetic energy is equal to 1/2 mv squared. So if we can summarize what we've learned in today's lesson, we can understand the interchange between the kinetic and the potential energy during simple harmonic motion when we understand the energy displacement graphs for a simple harmonic oscillator. So if we've been successful and we've learnt in this lesson, we should be able to detail the interchange between kinetic energy and potential energy during simple harmonic motion, calculate properties based on the energy stores of a simple harmonic oscillator, and understand and interpret the energy displacement graphs for a simple harmonic oscillator. So that brings us to the end of this lesson on simple harmonic motion energies, which is part of the oscillations topic in OCR A-Level Physics, Module 5, the Newtonian World and Astrophysics. Thank you very much for listening and have a lovely day.